This is OpenStax chapter 10, number 70. We're given a long, thin rod that's rotating about a point right here, and we're trying to figure out the moment of inertia, and they're asking us to do it using direct integration. Okay, so let's just slow down and set ourselves up for success. This is a mass that is distributed over lots of different points in space, so we cannot use the formula for moment of inertia that involves discrete masses. Normally, my next step would be to look it up in a table. And if the table doesn't have my exact shape with this exact point of rotation, then I would try the parallel axis theorem. And then my last resort would be to use integration. But this problem is telling us we have to use integration just so we can practice it. Okay, so let's look at our formula for integration. It says that the moment of inertia is equal to the integral of r squared dm. Don't just look at this formula and think, okay, these are numbers that I'm going to plug in and I know how to integrate. I want you to really understand what each of these terms means, because that's going to help you be able to set up an integral on your own. So whenever you see an integral, it says to take your thing you're looking at and chop it into tiny little pieces. In this case, each tiny little piece is going to be a piece of mass. And that mass is going to be, the individual chunk that we look at is going to have a mass of dm. For each chunk of mass, we're going to figure out r for that chunk. And remember, r is the distance from the mass to the pivot point. And then we just do r squared times the mass of that chunk. And then the integral says to do that for every single chunk of mass. That's what this is telling us to do. The problem is we cannot integrate over chunks of mass. When we perform an integral, we need to have coordinates that are our boundaries that we're going to integrate from some lower value to some upper value. So before we can even think about integrating at all, we need to set up a coordinate system. And the coordinate system is going to be what we use to tell people where are these chunks of mass located. So if I look at my mass that I have, I can choose my coordinate system to be whatever I want. I can put my x equals 0 wherever I want. And I'll tell you, it's easiest if you put your x equals 0 at the pivot point. So let's put that as our x equals 0. And then everything over here is like the positive x direction, and everything over here is the negative x direction. So my first step is to establish a coordinate system. Now that I've done that, let's look at a little chunk of mass. So right now, just hypothetically, I'm looking at this little chunk. We could have picked any chunk of mass to look at, but right now I'm just looking at this. What is dm? It is the mass. dm is the mass of this chunk. R is the distance from my pivot point to the chunk that I'm looking at. And then we can start to think about, where is the first chunk located? Just point to it. Where is the first chunk located? It's located right here. And where's the last chunk located? It's located right here. When we're talking about chopping this into different chunks of mass, and we want to make sure we include all of them. So now that I have a coordinate system, I can define the x position of that first chunk and the x position of that last chunk. So we can say that first chunk is at x equals negative L over 3, right? Because here's my x equals 0, so that's x equals negative L over 3. And the last chunk is at x equals 2L over 3. Those are integration limits. That's telling you where I'm going to integrate from one x position up to that final x position. That also tells us that we're going to be integrating over x. And what does x mean? X is the x position of the chunk we're looking at. So now that I know I'm integrating over x, I need to come back to my original integral and get each of these terms either in terms of x or in terms of variables that don't change when we look at different chunks. Also, we're going to need to get rid of the dm and write it in terms of dx, where dx is the width of that chunk. So first, let's look at r. R is the distance from the pivot point to the chunk. X is the x position of the chunk. How are those two values related to each other? Well, they're the same. If r is 1 centimeter and my x equals 0 is here, x is also 1 centimeter. So that's really easy. R is just equal to x because I put my x equals 0 at the pivot point. So that's going to be easy. I can plug that in there. Let's figure out how dm, the mass of that chunk, is related to dx, the width of that chunk. Well, we know the total mass and the total length. So I'm going to kind of set up an analogy. Whatever fraction dm is of my total mass has to be the same fraction that dx is of my total length. So let's say the mass that we're looking at, that little chunk, is 1/100th of the total mass. That width there, dx, would also have to be 1/100th of the total length. So I can write that as an equation. dm over m represents the fraction that this mass is compared to the total mass. Whatever fraction that is, we have to have the same fraction that dx is, that little width over our total length. And now we have a mathematical relationship between dm and dx. I can solve that for dm, and I'm going to plug in this whole thing into dm here. And now we're pretty much done with physics. The hard part of the problem is over. When you go to study everything up to this part, because everything that comes after this is just the algebra and the math. So don't worry about it. Spend more time studying everything up till now, okay? But the next step is going to be we'll plug in for x, we'll plug in for dm, we'll plug in our limits, and then we're ready to integrate. So here's my integral. My lower limit is negative L over 3. My upper limit is 2L over 3. Instead of r, I've plugged in x, so that becomes x squared. And then instead of dm, I've plugged in m over L times dx. And now we can bring out the ml, we can perform the integral, we can plug in everything, and we get that the moment of inertia is equal to L squared over 9. So we did it. Now they want us to check the answer using the parallel axis theorem, so let's do that quickly. Here's the parallel axis theorem. I need to take the moment of inertia as if the object were rotating through its center, and then add to it this little offset piece. So here's my mass that's rotating through that point. Here's my moment of inertia for the center of, if the object were rotating through the center of mass. I looked this up in the table. So that's going to be this piece. And then we just need to worry about the d. Let's find it here. There's the actual center of mass. That's just halfway across here. And d is defined as the distance between my pivot point and my center of mass. So let's figure out what that is. This pivot point is L over 3 from the end. The center of mass is just going to be at the center, which will be L over 2. So the distance between them is just going to be L over 2 minus L over 3, which is L over 6. So that's going to be the value of d that I use. And now we can put it all together here. So my moment of inertia, if it were rotating through the center of mass, is 1/12 ml squared. And then I'm going to plug in md squared, where d, I'll plug in L over 6. So that's what I've done here, and I get the same answer. Hooray!